The idea for this video is to take a look at the audio rate phase lock loops in Max. In the previous videos, which could be a good introduction to this, we built a phase lock loop that synchronized a phaser to an input phaser. And the idea for this video is that we instead want to build something that can synchronize to a general audio signal. Like, for example, in this case here we have a cycle object with a tone on 220 Hertz in this case. So this is just a simple tone, and we see the waveform and the spectrum here from 0 to 1000 Hertz. And it's a little bit more complicated in this case, because in the previous videos we synchronized to a phaser object where the phaser essentially gives you the instantaneous phase of the signal, whereas in this case with a sinusoidal signal we don't have direct access to the phase. So the main difference here is that we need to build a little bit more sophisticated phase error estimation algorithm. But to just recap from the first video, we have an input signal X, which in this case is a sinusoid. And in our PLL we have a numerically controlled oscillator. We compare the phase of our NCO with the phase of our input signal, and we have some kind of control loop that updates the NCO based on the error. And here we can start with building this NCO. So let's use, for this case, a Gen tilde code box. And this is very similar to what we did in the first video, where we have a history to keep track of our phase, and we have a parameter for the frequency, and we can set this to 220 by default. And now for every sample we update the phase with a small increment, which is the frequency divided by the sample rate. But now we want a sinusoidal output here in the output signal. So in this case we want the phase to go between 0 and 2 pi, and then we can use a lookup table, essentially the cosine of the phase. And if we copy the visualization part here, we have exactly the same signal in the output. And we can also change the frequency like this. So this is very simple. We have the NCO. And now we want to compare the phase of this NCO with the phase of the input signal. And the way to do this is, or one way to do this is using what's known as a complex oscillator, which has an in-phase and quadrature component. And this essentially means that we have an I component, the in phase, which is exactly this cosine signal. And we have a quadrature component, which is 90 degrees out of phase with the in phase component. And this is typically defined as minus sine of the phase. And what we then do to get a measurement of the phase offset between these two signals is simply that we make a frequency multiplication with the in phase and the quadrature component. So we need our input signal, let's call this x, and we have already connected this here. So x will be this input sinusoid. And we multiply NCO I component with x and the NCO Q component also with x. And let's now try to output these two signals. And let's use, for example, a live.scope. So this is our MI, and this is our MQ. And now we observe something, that we have some kind of stable offset here, and then we have a high frequency component. And if we also duplicate this spectrogram and look, for example, at this first MI, we see that we have a DC signal here, and we have some kind of higher frequency as well. And this is exactly what happens when you multiply two sine or cosine signals, that you get one component which is the difference in frequency and another component which is the sum of the frequencies. So in this case 220 plus 220, so this peak is at 440 hertz. And if we deviate the frequency, we still have this sum of the frequencies, and this difference of 1 Hertz here is what we see the low frequency component. And as soon as we have them in the same frequency, this low frequency component stops moving essentially. And this low frequency component is what we're interested in, and the high frequency we want to filter out. And of course, one way to do this is to use a low pass filter. So we want some kind of very low frequency low pass filter to take away this high frequency component and just keep this close to DC component. So we can use a one pole low pass filter. Let's call this M low pass I and M low pass Q, one filter for each component. And then we also need a frequency for this low pass. Let's set this maybe to 10 Hertz to start with. And then this coefficient for the low pass filter is exponential minus 2 pi times frequency divided by sample rate. This is a fairly standard definition of this coefficient in a one pole low pass filter that you can look up in any type of implementation of such a filter. And the filtering itself is that we average the multiplied output so the output of the low pass is alpha times the previous value plus 1 minus alpha times the input. So now if we output this low pass version, you see here that this higher frequency peak got attenuated slightly. And if we take this parameter, the low pass frequency parameter that we created, let's see. Now something is wrong. Maybe I mixed up. Should be 1 minus alpha I see. I put the wrong parameter in the computation of alpha here. It should be the low pass frequency. And then it should probably be like it was before. Alpha times the old value plus 1 minus alpha times the input. There we go. So now you see that as we reduce the low pass frequency, we cancel this higher peak and this output becomes more close to a constant. So then we need to also apply the same thing to the Q component. So MLP Q, we update the filter in the same way but with Q as input. And then we also output the filtered Q output. So now essentially we have this I and Q component in output, and a common way to visualize this is like a two-dimensional plane where we have I and Q on the axis like this, and our signal will sort of live on this unit circle, and the angle here is the phase offset between the input and the NCO. So if we want to visualize this in a more clear way, we can copy the scope object here and set this not to automatic mode, because then we have this X and Y scope where we can input an X signal and a Y signal and visualize this in exactly this 2D plane. But now we need to also reduce the buffer size and the number of samples per pixels. And now it's not super clear, but there is a dot here in this plot. And if we deviate the frequency, you see that this output in the I and Q plane starts to rotate. So this is measuring now the phase offset between these two sinusoidal signals. So we can get rid of this. But this is a two-dimensional output, so it's still not a measurement of the phase as a scalar value. But of course, we know here that when we are on this circle, we have a triangle here. So we can get this angle. So the angle is the inverse tangent function of the X and Y component, which is our I and Q. So let's try this. So we say that the error is the A tangent, and in gen tilde this can be computed with the ATAN2 function, which takes the opposite side of the triangle as first argument. So this is our Q component, and the closed side of the triangle, which is our I component. And now if we output this error, make a live.scope, we see this phase offset, which is actually between minus pi and pi. So we need to adjust the scale here to minus pi to pi. So we have the phase error I and Q component, and then we have the phase error in radians, like this. And if we set the frequencies to be the same, you see that this phase error stabilizes. So now if we want to lock the phase, we can do exactly what we did in the first tutorial. We do proportional control of this NCO based on this phase error. So this, if you recall, was that we every sample adjust the phase with some small value, small constant k proportional times the error, and we need to define this. So let's pick some small value like this, and then you see instantly this phase error locks to 0. And I mean, if we listen to this signal, we have the sinusoid, exactly like the input. But this, from an audio perspective, is not very interesting because our ears don't really perceive phase unless there are multiple signals which are in or out of phase with each other. So changing, for example, the frequency of the input here will just make this signal slightly wobble like this, and then as we go to the same frequency as the NCO, we are actually locked in phase to this input, but we don't really perceive this effect. Now, assume here that we want our NCO to not only track the phase of the input signal, but also track the frequency of the input signal. Then we need to build a slightly different control loop here. because the proportional control here will only adjust the phase when the frequency of the NCO is the same as the frequency of the input. And there is a quite good article on this Wireless Pi website which explains how this works in wireless communications, but the principle is essentially or exactly the same. So you see here the construction here is the same, a phase error detector, there's a loop filter, there is a control of the NCO, and the difference here is that we have so far only used this proportional control, but for a more general phase lock loop we also have this integrator control, which is integrating the phase error over time and also using this to adjust the phase of the NCO. So you see there's a constant Ki here, and then this is averaged with a delay of 1 over time. And this article overall is very good for explaining all of these things. We can of course not go through all of this here, but if you're interested, I will also put a link to this in the video. But the main thing here is that this integrator control is something that allows this PLL to also track the frequency of the input, because essentially integration of phase is frequency, because phase is derivative of frequency. So this means that they here filter the phase error with this K integral term as well, and then use a sum of these two to update the NCO. And let's try to implement this. So we already had the proportional control here, but let's then add yet another history that we can call integral, and then here we can define a K integral, which is typically a much smaller value, but we will go into how to set this properly in a minute. And then for every audio sample in our loop here, we update this integral value with this factor times the error. And exactly like they described in the article, we update the phase with the sum of the proportional term and the integral term. And now this can easily become quite unstable because it's very sensitive to what parameters we choose here. Maybe let's try a smaller value. Yes, okay. So now you see this phase error locked in when we are using some other parameter. It is sort of confused how to lock into this input, but setting some more correct value, we see that we smoothly start to lock into the input. So now I think we should be able to also adjust the NCO frequency. You see that the output here is now tracking the frequency of the input. But if I move this too fast, then it becomes confused. So it's very sensitive to the parameter settings. So then the question is how to set these parameters to get something that is kind of reactive to the a bit more fast frequency changes in the input. And for this video, we will not dive deeply into how all of these things work, but from the article here, it's quite useful how they describe how to design a PLL. And the main parameter is this dampening factor, which will adjust essentially how fast or reactive this PLL will be over time. So a lower dampening factor will sort of slowly ramp in with some overshoot, and a higher dampening factor will lock in faster. And if I remember correctly, they have some approximate equations here where they say that usually a good balance is achieved with this 1 over square root of 2 for the dampening factor. And then they have this constant Bn, which is the loop bandwidth, which is essentially, if I understand correctly, how wide frequency changes the PLL is able to adapt to. So we can compute this in Max to set the parameters in the gen tilde to match this. And one good practice perhaps is, if we do this inside gen tilde, of course we can do that, but it's a little bit unnecessary from a CPU perspective, because we only need to compute this once and then we can set this k proportional and k integral as constant inside Gentilde, so we don't compute those constant for every loop of the audio processing here. So let's do that outside in regular Max. And let's call this our dampening factor. And this our loop bandwidth. And let's pack these two into a list. And then we want an expression but let's compute kp here without the fs. So for the kp we can, I think, probably skip these loop gain parameters for now. And let's take 4 times this dampening factor, which is our first float in the list. And we divide this by dampening factor again, plus 1/4 times the dampening factor, and then times the loop bandwidth, which is the second object in the list, or second float in the list. And let's leave the gain parameters to 1 for now, and then let's divide by fs inside the Gentilde. So now if we try, for example, with the square root of 1/square root of 2, like they suggest, and maybe a loop bandwidth of 10, we get this value. Let's do the same for the ki term. Then we have just 4 divided by the same thing but to the power of 2. And then times the loop bandwidth to the power of 2 as well. And then we should get some other constant here. So this is essentially to get some simpler high-level controls, which then gets translated to these constants that we use inside the audio loop. So here we can create parameters. And maybe initialize them to 0. It doesn't really matter. And now outside here we can prepend the parameter name and put this as input to our gen tilde code box. Now these don't show up. I think there is some error in the gen tilde code. Aha. I cannot set these when they are parameter names. So let's call these kp and ki. So essentially when I defined the parameters here with the same name as the variable names, gen tilde started complaining. So we renamed this kp and ki and just replaced the variable names here. And now we can see the parameters k proportional and k integral are updated based on our equations from the article here. And then we can set kp, which is this constant that we computed, but also divided by the sample rate, and ki will be k integral, our parameter that comes in, divided by the sample rate to the power of 2, like that. So now let's try with the 1 over square root of 2 and loop bandwidth of 10 and listen to the result. So you see it's a little bit more responsive now. And if we increase the dampening factor, should see a bit faster response. And then you hear this phase noisy result when we move the frequency too fast and the PLL gets confused, and then it takes some time to recover. And this is essentially like the basic implementation of this, and the useful thing now is that, for example, if we have an input which is not sinusoidal. So let's take a rectangle, like a square wave. So our input is this non-sinusoid waveform, which has overtones, as you see. The PLL can still track the fundamental frequency of our input. And even, for example, if we try here adding some noise to the signal, some scaled noise, you hear our input is square wave, a noisy square wave. And we are still tracking the fundamental of this input. So I think that is all for this part of the tutorial. And then in the next part, let's look at some tweaks to this to get some more musically useful results from it.